updates. Yes, let's do. This is a test. Yeah, good. Ready? Yeah, sure. How's the answers? All right, let's start. So this is the last lecture in our Python mini course, and by popular demand, it's going to be about pandas. Pandas not being the cute bear-like creatures from China, but being a package in Python that is particularly handy when you're doing data manipulation. And since a lot of science is done with data, yes, this is not inappropriate. So today we're going to look a little bit about data analysis and manipulation, a little bit more general than and diverting a little bit from the numerical sort of bias we've had in the last few lectures. So anything that is not an n-dimensional array is still data and might still be something you have to look at. And so we'll look at the Pandas perspective. So let's talk a little bit about data analysis and manipulation, sort of in general, in the sort of the current trend of data-oriented science. So when you have data, and this has always been true, there's a couple of tasks that are very common. First, the data is given to you, or you record it somehow in an experiment in a format. You usually don't have that format under control, so the first thing to do is to get that data out of there and to understand how it's written. Then your data might not be perfect, especially if you're collecting it in the field, or even if not. So there'll be some sort of cleaning or combining data. Maybe this is not all the data. Maybe you want a subset of the data. Maybe you want two data sets or them together. So the cleaning, combining, etc., is another part. And then once the data is sort of in your environment, so in our case in Python or IPython, you probably want to, okay, there's my raw data. Now I want to create something that I'm really interested in. I'm going to derive either some things, take averages, do some stats on them, do some computation on them, maybe model, find a model that works, or run a model that will generate the data. This is not necessarily a linear regression. These are just tasks that are involved in data handling. And usually at the end of the day, when you have done your data, you want to present this. So this might be as simple as, okay, what was the mean of my data, or some plot, or any sort of way of presenting the data that gives you some insight or communicates that insight to other people. So as I said, this is not a linear sort of progression, because if you're generating data, you kind of start at point 4 But it's just to show that in these 4 short weeks, we have covered some elements of points 1, 4, and 5. We've done reading and writing. We've done modeling and computation. Last time, for instance, we did ordinary differential equations where we solved an equation. We generated data there. And we've done some visualizations, so we've done point 5 for sure. But we haven't done much about cleaning data, combining data, normalizing data, or creating new or derived data out of existing data. And so that's what this lecture is essentially about. At least one way of doing this. And doing this with rectangular arrays is not typically, it's not always the way, because that might not be how your data comes in. So if your step 1, if your file format is fairly irregular, we'll have to have a way of handling that too. So we can't always straight away go to a NumPy array and say, hey, this is the best way to do it, because that might not be how things come in. And it might not even be how it's really structured. So when it's not a nice 2D, 3D, 1D array, you could call this unstructured data. And so we've been focused on regular arrays, which is very common in scientific computing, but that's not how all data looks. If you've got patient data or any sort of records, or weather information from ships in the 19th century, data that comes that you scroll from the web. I mean, in all kinds of, there's data of all kinds of form, and even if it is sort of array-like, or you made it array-like, there might still be something where you still have to go over and select parts of the data that you're interested in. You might have missing data, so you might have to deal with that. And sometimes, even if it is rectangular, it might not be the best thing to just enumerate the axes from 0 to n and 0 to m or something. Sometimes that's just not natural. So we're going to look first at a few handy ways to organize data in Python when you don't have this, when you don't have the NumPy format. So before we do that, I just want to mention that unstructured data does not exist. The only real unstructured data is random noise. So what we mean with unstructured data is really that it's not simply structured as a multidimensional array, or that it's given in some text format that needs some parsing, but there is a structure there, right? Otherwise, there'd be no meaning in it. It's just harder to get that structure out. So the first step when you're dealing with unstructured data is just to make it structured. And you're not losing anything there. That's just getting the structure out that's in there to begin with. So another often mentioned phrase these days is big data. Everything is big, right? Data is big, it's growing, we can't handle it. It's a new era, everything is data-driven. Now, but then what is big data would be? When is it big? Nobody agrees on. Big is relative. And there is really no such thing as big data. Do I care that there's 1 million records if it still takes me 1 second to process it? No, that's not big data. So whether something is big or not really depends on whether you are at a point where, I guess, your Excel sheet just doesn't cut it anymore. Are you at a point where either the analysis is too complex, or the sheer volume is too big, or the data itself is very complex? That's what makes it into big data, not the fact that it's a lot of it. All that does is make your statistics better, but that's not what people mean with big data. Now, there is a lot of data out there, this is true, and it is growing. So, and a lot of the data is not a NumPy array. But still, a lot of data can be thought of as tables, as sort of organized properties of objects, etc. And we'll see that in some sense, you can almost always make that into a kind of tabular form. So if you had a table is a little bit more general than just a 2D array, right? Because you generally have columns and rows, and you label the columns because they mean something. You might even label the records by something other than a number. And these columns typically don't have all the same type. So think of a typical spreadsheet. You might have some numbers in it, but also names, student ID, grades, like different types of numbers in there. Again, this deviates from just a simple 2D array. And then there's all kinds of ways these things can be formatted as like different file formats, comma-separated values, Excel sheets, text tables, HDF5 files. Like there's a big mixture. And so the fact that this is a mess is maybe what makes it mostly big. So still, sometimes these things are not as structured. And so what are some of the options we have in Python to represent data like that? Let's first look at one particular type of data. Some random information here, somebody's name, somebody's age, and their height, eye color, and who they work for. It's a bit of information that not an array. That's not all elements are the same. It's not a list, because each bit of information is useless unless I know the label that's in front of it. If I don't know that 43 is an age, that number has no meaning. It's not just unstructured, it is meaningless. Now, I could think of this as two lists, one of the properties and the other of the values of the properties. But it's vital or essential in this bit of data that these two are linked, right? So if I remove one element from the right list, remove green, then the eye color shouldn't become SINET. So this link between the key and the value is very essential. So this is a typical key value store, a key value structure. Other words of it are records, but it's just there's different values. The values have different names, and there's a structure for that in Python. It's called a dictionary. I think we briefly mentioned it already. So it's a very common format. With every key, there's a value associated, and the values don't have to have a specific type. So to work with dictionaries, to work with these sort of key value things, is fairly simple. There's a variety of ways that you can start them, but dictionaries, when you print them, will have this curly brace in them. That indicates that it's a dictionary, a key value dictionary. And so one way to do it is just give the dict a number of labels, 1, 2, 3, and give them values, so 1, 2, 3. And so the labels become strings if you do that. But they don't have to be strings. Okay, they can also be numbers. You can also give it sort of the dictionary format, so curly braces and then colons to separate the key and the values. You can make an empty dictionary, and once you have an empty dictionary, you can actually put things in this dictionary just by pretending it's already there. So these square brackets look up the key, right, the label of your value, and then give back a handle to the value. So you give it the key, and then C of 1 is pointing to the value. So I can set the value to 1, even if it didn't exist yet. It just dynamically adds a property called 1 that has been assigned the value 1, and the same for 2 and 3. So if I print C after that, it will be the same dictionaries as A and B in this case. So I can do this dynamically, and that's kind of nice. One of the nice things about dictionaries is that I can put in it what I want. If I need to put more in it, that's fine. There's ways to delete things from it as well. So it's very flexible. But this generality, of course, comes at a cost. This is why we're not using dictionaries. This is why we're not even using lists when we are doing numerical stuff. And so we'll see there's performance gains if we go beyond this. But this is what's standard in Python. And sometimes this is all you need. So you can get all the keys out by doing .keys. You can see if a key is in the dictionary by saying the name of the key in B, and then it's true or false. You can do fancy things like setting defaults if you add new things. It's kind of nice. You can get your stuff out with this square brackets notation. So one sort of generalization in which this structure doesn't work as well anymore is when you have key value stores. In other words, what if several values are to be associated with one key? And what if those values have to be able to be of different types? So for instance, I have a list of buildings, and I want to know what their color is, when they were built, where they are. Basically, a table. So if I have a table like that, I have a key, that's the left column here, house, office, shed. And then with each of the key, there's a value associated, but not just one, there are several. So there's a color value, there's a build value, there's a where value, which I haven't filled in. So it's like the key value, but each of the values are a list. Now, I could do that, right? I could just say, well, since I could put anything in the dictionary, I can put lists in there. But you can imagine that kind of that sort of recursive structure is not always ideal, and it's hard to impose that each of the rows has the same type of columns. Right? The dictionary in that case is a little bit too general. So this table kind of form is so common that this is a structure that's been used for decades, and I don't mean this loosely, many decades, and they're called relational databases. They are built out of these kind of tables. There'll be tables and other tables that point to other tables, et cetera, et cetera. And they're a very useful way of thinking about data. And they have a name of not being, or a reputation of not being very high performance. That reputation is somewhat incorrect. But they got this from the idea of there's big data and it doesn't fit in databases anymore. If you have anything under 1 million records, any decent database will be just fine for you. And 1 million isn't little, right? So, but it still has to be tabular, and you still have to deal with sort of an interface between your database and your programming language. Now, in other words, in Python, you don't have a relational database type. You don't even have a table type so much. You have the NumPy arrays now. These aren't built in, but they are there. Everything has to be of the same type. You've got your dictionary. So there's going to be something that goes beyond that has this tabular form, and that will be Pandas. So we have different kind of values. So NumPy arrays are no good. We could have dictionaries of dictionaries or something like that, but that's wasteful, inefficient, and hard to sort of ensure everything has a build value or a color value. We could store each column as a NumPy array. We could do that, but then we get the same problem where the association between keys and values isn't necessarily automatic, right? And we don't have some of the nice labeling capacities that the dictionaries have. So we want something that can label columns, where columns can have different types. I want to be able to even label rows so that they can have different keys. So all of that is possible using the data frame data type from Pandas. So if you have any unstructured data, say a bunch of records, and some things would mention perhaps where something was built and others might not leave that, give that information, you can still put it in a table like that. You just have to have a way to say that a certain bit of information is missing. So even when it doesn't look like it's a table, oftentimes you can still put it in a tabular form. Not everything, but oftentimes this is the case. So it's a fairly generic way of storing things. And that's why Pandas is good in dealing with a lot of different data. Any questions about sort of the general idea of different data types? Okay. So the whole thing in Pandas revolves around these data frames, which are essentially tables. If you know a little bit of R, you know there's data dot frames in that context that are sort of the same idea. Pandas is to some extent sometimes called R data frames on steroids. I don't know if that's fair, because on the other hand, Pandas doesn't come with the whole host of statistical analysis tools that are built into R. So it really depends on what you need. But it is very powerful, and it's built upon NumPy. So where it can, it will use a NumPy array under the hood, so you get that performance boost. It's thoroughly tested, so that's it's a big bonus. You can be fairly reliant that it's working. The API, which stands for Application Programming Interface, which means the way you use it in Python, is relatively easy. And after a while, you sort of have an intuition about it. It doesn't take too long. Another thing that it has is excellent support for many input and output formats. So it can read a comma-separated value file. It can read an Excel file. It can read an HTML5 file. So that's just built in, and that means that you don't have to spend as much time sort of reading your data and figure out. You still always have to check that what you read made sense, but at least it gets read. You probably have pandas in the canopy installer. If not, you can do a pip install in the prompt, but it shouldn't be too hard to install this. I think I did pip, but it could all be in the installer. And there's a website that explains everything about pandas. So I could stop there, but I won't. So it's a big package, all right? It didn't start big. It started to be, or the aim was to make it sort of easy to use, and just a few techniques. But there's a lot of things you can do once you have your data structured in this sort of tabular form. And so what I'm going to do is I'm sort of mostly going to look at some examples, and you'll see the hopefully the value of or the ease at which you do things in pandas, even if the syntax might not be completely understandable in every sense or in every slide in detail. So pandas, that's the package. Conventionally is imported and abbreviated as PD just for no particular reason, as laziness of typing. And so this slide actually doesn't use pandas. It has the import statement, but that's more of a mistake. Everything here was not done with pandas yet. We're trying to make a table first. And we're doing this here in pure Python. So the table will have names: Anna, William, Emma, John, James, and Mary. It will have genders, indicated by a letter, female and male, and then numbers. These are just lists, and I want to make them into a table. I can use a nice little function in Python called zip, which zips them together. That is, it takes all the first elements and puts them in a tuple, and all the second elements of the list that you give it, and put those in a tuple, and then you get a list of these tuples. So Anna was female and had some sort of number of 2,604. William, male, etc. So I've constructed a table. Now, it turns out, or these numbers weren't random. These were chosen or taken from some sort of list of the top 3 American girl and boy names in 1880. Something that helps to know that the data is something. And so these numbers, yeah, that could be. I guess that's how many were born in 1880 with that name, or at least kept record of. I'm guessing they were not all reported. Sure. No, it's all Python. So this part is still all Python. But this is a tuple, a list of tuples. There's no real way. I've constructed it with zip, but I don't. Once the structure is there, I can't do much with it except it's there. The tuples are immutable. I could add a record. You can do that with list, but I could add something to that list that doesn't even have that form. So there's no inherent structure to this. I just created it so that it looks like a table. To sort of enforce the structure, once the structure is enforced, allow a whole bunch of functionality, I can use the data frame from Pandas. So that's what's going to go on here. So we'll take that data we just created, and we give it to the data frame generator or constructor. So df becomes the data frame, and I give it the data, and I give it names of columns. So these had columns, but they didn't have names yet. It would be nice to have them have names, in this case, name, gender, number. So the meaning is apparent. Then if I print that data frame, it will have a table, but now it'll have a table where everything is labeled. The name columns, gender columns, number columns, but also the records themselves are labeled. In this case, they're labeled just by enumerating them from 0 to 5. That's the default. But you can give a list of names as well for the key for what's essentially the keys. So this is a key value store where the keys in this case are the integers on the left column. Pandas calls these keys indices. So I'll talk about indices. So it's an index, and at this point it's just a number that's assigned to it, but it can be kind of it's very useful because they've become labels. Just a little aside, or a little demonstration that Pandas works well with a lot of different file formats, even Microsoft Excel sheets. So I could write to an Excel sheet, and I could read from them too. You need a few extra Python modules for this to work. If you're dealing with these, I list them there, but just for your convenience, if you're so inclined, or if one of your collaborators is unfortunate enough to use Excel and not Python or R or something. Okay, so we have a data frame, things are labeled. Other than that, we haven't really seen much use out of it. It was nice, things are labeled, but that's fine. I knew what they meant anyway. Let's just look at a few functions and see how we can use this stuff and how all of this labeling is actually useful. So one thing I can do is I can ask, I can access each column doing the same sort of key value dictionary syntax, square braces and square brackets and the name of the key or index. And so in this case, the square brackets by default look at the column name, so they pick out a column. So square braces, rather than picking one of the keys, pick a column. So they pick the name column if I do df name, and then I can ask that column to describe itself. This is this sort of object-oriented stuff, right? You do a dot, and then it describes itself. So it describes itself. It says, okay, well, I count 6 things in my column. 6 of them are unique. The top is Anna, and the frequency is 1. That's not true because they're all frequency 1. So this is just sort of random in this case. But if there were a top, you could see the top. You can and then it has a few information about what the name is and the type. When you get a column, just a single column, that's not itself a data frame because it's just a single column. There's a special type for that, and it's called a series. It's just useful to know if you look at the documentation. So single column is a series, and the nice thing about a series, rather than being a single column, is that it has those indices still attached to it. So those numbers are still there. So you take df name, and if you just printed that, it would give you the number 0 to 5 and then the name. So it's sort of a short form data frame. It's called a series. In many cases, they look very much alike. So I can ask name to describe itself. I can ask number to describe itself. And this is a different alternative syntax where I just treat number as a property of the data frame. So rather than doing square brackets, I just do df.number, and I'll have that describe itself as well. This is now a numerical type, and because it's a numerical type, it describes itself a little bit differently. It right away says, okay, yes, I have 6 things in me in this column, but I'll compute for you, since you want to describe what I am, I'll compute the mean and the standard deviation and the minimum and some quantiles and the maximum. So it'll give you some brief statistical information on what's in this column, just because it's numerical. So each column has the same type. The different columns don't have to, and that's why it can describe itself better depending on what it is. If it's just text, it'll do the top. If it's numerical, it'll try to give you some numerical statistic. Now, I can ask things like sort yourself according to a column. So if I want to sort by number, I probably want to know which one's the highest. Then I get back another data frame, and I could print the first 2 of that by doing head. So sorted is another data frame in this case. So sort gives back a new data frame called sorted in this case. And then .head 2 gives the first 2 of that. So because it's numbered, it will give you the first 2. Now it's sorted, but it sorts it in ascending order. So these are actually the least ones. I can count specifically how many are. That's the same as the count gives in the describe. But if I just want to count, there's a function for that. I can ask the shape of the data frame. This is just how many rows and columns there are. I can ask for the sum specifically. So rather than have that wasn't even in the description, but that's sum. I can ask the types of the different columns. So it'll tell me name is an object, gender is an object, and number is an integer. So it does object, but it isn't quite sure what it should do. And apparently a string becomes an object. Very well. So there's all kinds of stuff that's built into this data frame. Ways to select columns, get information about columns, and sort things by a specific column. I can add columns too. That's kind of nice. So maybe at some point I decide, okay, I have all this information about buildings, and now I also want to know if they have a flat roof or a pointy roof. That's a new column. So adding a column, I just first have to make that column somehow. So here's a column D, 0, 1, nan, and 2. Now nan, when we're talking about it, is the way that Pandas describes missing information. So if it's missing, you put a nan there. Nan is not a number. That's sort of inherited from NumPy a little bit. But that's how it indicates that. So you can have missing data, and there's ways to deal with the missing data, filter it out, replace it with a default value. All of that can be done. But for now, let's say it's missing. And then I can make a data frame out of that just by giving it that. And you see that became a column that is now indexed from 0 to 3, and the nan is still right there. I didn't give a name to the column, so the column name is just become 0. Sure. Now, I can change that column name by assigning the .columns property of the data frame and just give it a list of all of the names I'd like the columns to be, and I made it into rev. Maybe it's revision. I'm not quite sure what it stands for. And then if I print it, that's the label that has become. And I can do some other nice things, like maybe I want to print out a subsection of the row, so I can do slicing with the square brackets. And this is a little bit tricky because it slices rows, but if you just index it, you get columns. So I find this mildly confusing. So this just gives me from 1 to 2, but remember, all those ranges in Python, the last one you never get, so you don't get 2. So give me 1 until everything just before 2, which means just 1. So that's what you get. Now, this slicing still gives you back a data frame, right? You still have the label. Everything maintains its label unless I specifically ask to only get the values. And that's a good thing. I can set the value of a column. So if I add a new column, I don't actually have to add it. Like with dictionaries, I can just start using it, and it exists. So df new column is 5 means I assign 5 to all of the entries of a new column called new col. And when I print df, the new column has appeared, and they all have the value 5. I could assign it to an array as well, and then it would have different numbers. There's a variety of things you can do there. I can create yet another column called test just by assigning it a value. In this case, I assign it the revision column plus 1. And so sure enough, it added 1 to each revision. The nan stays a nan because if it's missing data, then missing data plus 1 is still counting as missing data. And then I can just get the test. And I think this last row should have been there too, but it fell off the slide. So lots of things to manipulate columns, add columns, create columns. Very similar to dictionaries. And one of the nice things that this Pandas data frame does is that it's kind of a 2D dictionary. It's a dictionary in one direction. I could say, well, there's indices here and there's names on that, and I could use both. Now, if I just wanted rows, because for now the default is just to use columns when I do the square braces, I can just get columns as well. So I can access columns with this access function, and I can ask for, or access rows, sorry, with this access function. You can just ask for the third row, or actually the fourth row. Row number 3 it starts at 0. And then I'll get just a list of the revision, new column, test. And so, yeah. So that's just one row. I can get one row out. I can append rows too, but I have to be careful here. So I should have done this in 2 steps. But suppose I want to append a row to the table we just have. So I want to create a second data frame called data frame 2, df2, by appending this same row once again. So I do that df.append, and then I have this extra option, ignore index equals true. And we'll see why we need that in a second. But it does what it does, right? So it adds another one of those three, a copy at the end. Then it became the one that's indexed 4. Just added a row. When you add things, they're supposed to be data frames or series. That's the best way. If you don't, the right-hand side stuff can happen. So I've decided to append yet another row called, and the row is supposed to contain -1, -2, and -3. And if I just do that without this nice ignore index option or without even specifying anything, what I get is that I get 3 new columns. And that's because these things weren't labeled and didn't say in which columns these numbers should go. So it goes, well, if you don't give me a label, I'm going to make up labels. And I start making up labels by numbering them from 0 to 1, 4, 2, etc. So it created a new column for the -1. I call that column 0. A new column for -2 and a new column for -3. The only row for which there are any values specified is the last one. That's the one I just added, right? So that's there. And then all the other ones, I don't have any information for those rows, so those all become nouns. It's an even bigger mess because I also didn't say what the index is of this row. And so the index is still 0. So I have 2 rows here whose index is 0. That's not generally a good thing. It's allowed because sometimes it's just how things, I guess, end up. But it makes things less efficient. If you're going to look for element 0 and you know there's multiple ones, you're just going to have to look through the whole thing until you find all of them. So you don't really want that. So there's 2 things going on. First, this last one, which I mentioned, that your index is still 0 because I haven't specified what the index was. And that's why you need the ignore index in this case. If I hadn't done that here, this guy would have been 0 also. Okay? The 4 in this little corner would have been 0 as well. So that's an easy problem. But getting these new columns, or making sure I don't get these new columns, I will have to say what these numbers mean, what the labels are. So if I give the column labels with the append function, then I tell Pandas that -1 means the ref column, -2 means the new column, -3 means the test. It even means that I could mix up the order as long as I have the columns correctly. And that is why you do this. That's why you do labeling. You might want to combine 2 tables that have the same kind of columns. They're just ordered differently. Right? You don't have to worry about that. You could add those. You could merge those together just because the labels will be matched rather than just where the data really is. But because of that, when you don't say what the labels are, you get this kind of. So when you say what the labels are, here we go. We get the right answer. I still haven't given it the ignore index, so I still have the 0 issue here. So if I also added ignore index, I would get a nice new index 5 there. Okay. So there's a little bit of carefulness there. If what you're appending is already a data frame or a series, like the stuff we get from the access function, we didn't have to worry about much of that. So all these labels that come out, I put them back in, everything falls in the right space. If I added this to another table that just has a whole bunch of columns and also columns of these names, I could just append this row and put them in the right spot, and the rest would be nouns. Okay. So it's a really good way to keep track of what this data means just by having it labeled. Okay, so that's kind of the basics of the data frame structure itself and how you interact with it. But you don't really see what it can do unless you look at a real example. So we're gonna try and look at that. Real data. You can play along if you want. There's a file called 311 service request.csv.zip, which is zipped, and if you unzip it, you get a comma-separated value. Put it somewhere. We'll see how to work with it. This is actually the service request data from New York City in some period. I forgot which period it was. I think I took a subsection because it was too big to do everything. But by the way, Toronto now also has open data, so New York City was a little bit earlier, but I'm not sure if this precise data is there, but it might well be. But this one is from New York City. And so when you start with a new set of data, you kind of want to look at it first. Now, comma-separated values are text formats, so it's kind of nice in the sense that you could look at it. But if this was a 40-gigabyte file, you still don't want to open it in an editor and see what it is, because it will take a long time just to read it in for no particular reason. But you could use other utilities that just like print the first few lines. In Linux, you'd use head or something. If you don't have that, or if it's a binary format, you can still read it in. And that's one of the strengths of Pandas. You just say, OK, Pandas, here's a comma-separated value. So let's put that in a data frame with the function pd.readCSV. Give it a file name, and it starts reading this. I can ask what the shape is. So now I know there's about 100,000 records, rows, and 52 columns. I can ask the data, what are your columns? So data.columns. So format is a little bit funny because of the automatic coloring, but they're all strings. Okay? So there's a column that has a unique ID, when it was created, when it was closed, zip code of the incident, the address, street name, community, borough, school, city, school, state, all kinds. Right? And just to get an idea of what it means, because sometimes the label isn't quite clear, but seeing what kind of values in there might help, we could use we could look at the values just of the first row. So .values gives you just a handle to the values. Now you've lost this labeling stuff, so you don't use that very often, unless you want to say pass it to a NumPy function or something like that. So here are some values of the first row. There's a number, there's a date, some missing data and every now and then, and my PD, you can guess what that means. And what type it is, noise, street, sidewalk. So you can kind of interpret a little bit what this really means. We could look at just the first 3 rows with this slicing, as we saw before. So let's just look at the first 3. What it does is if things do not fit on the page, it just starts printing the other columns and more columns and more columns. Because it has the indices in the front, you're supposed to think of them as all concatenated, right? So everything of 0 belongs together. So we're going to look at complaints. And we're going to look at particular complaints. So we want to know what type of complaints there are. They're encoded in some sort of string, but it's been done fairly faithfully so that the string is always the same. It's been uniformized. So we don't have to have much of data cleaning in this case, where so here, for instance, a complaint type called illegal parking. There are no cases where that is filled with illegal parking, with parking has a lowercase or something silly like that that would sort of mess up some of the analysis you might want to do. But that's for this particular set. One would have to check. So we can check what the unique complaint types are by saying, by using NumPy's unique function. That's kind of nice. And so I get the data out of that column and just the value. So as I said, when you're going to pass something to NumPy, that's when values can be useful, because NumPy doesn't know how to deal with data frames, but it doesn't know how to deal with arrays. So this is given to NumPy, and oh, I didn't have the output. Well, you can try that. So basically, you're going to get a list kind of like this with no duplicates, noise, illegal parking, noise commercial. We could ask to have just some of the columns, and even just some of the columns and some of the rows, sort of carve out a rectangle or a selection out of this. So you could do that with a lock function or object. And the first range gives you the rows. Whenever you have this sort of slicing, it's rows. And then the next one gives you all the labels of the columns I want. And here's just a sort of random subsection of complaint types, when they were created, and where. So let's suppose we only want the noise complaint data. Well, there's a very nice way we can do this. So we can get just the noise data. So sort of a sub data frame that only contains the noise data by selecting from the data anywhere where the complaint type column is equal to noise speed sidebar. And when I do that and I just print out, say, the first 3 rows, that's what I get. They all have the same complaint type. It's a very handy way to pick out just those rows that have a particular value for a given column. You can get the shapes, so there's just under 2,000 of these in here. And this works because I can do this sort of comparisons on a data frame, or of a column actually, where I say, okay, I have my complaint type, and I want to know when it's equal to noise. So this first type, the first part of this, or the left-hand side, so to speak, is a series, right? That's a column that we got out of there. And the other one is just that series, element by element, compared with noise equals type. So what it gives back is another series of true or false statements that says whether or not this is valid. So this in itself is an array of Boolean values. And that array of Boolean values I can give as an index to noise. So data, and then I give that Boolean in there. Sorry, this noise is a list of indices. And then all of the data is given by giving the data between square brackets, give that Boolean array. I can do even fancier things. I can combine all the data, all the rows where the complaint type is noise. So I can have one Boolean array for that is noise, and where they occurred in Brooklyn, another one in Brooklyn. And those are 2 Boolean arrays that then I can combine with the ampersand, which is the AND function. So true and true is true, true and false is false, false and false is false, which gives me all of the complaints of noise on the sidewalk in Brooklyn. So I can do very fancy slicing and dicing by values and by the labels of the columns. So let's figure out who complains the most. So I look at all the data where it is noise, and so noise, I can look at the boroughs, so the different boroughs of New York, and see where most of the complaints came from just by counting the number of values there. So value counts just counts the number of occurrences of unique values of that column. And, well, if anybody expected that, but Manhattan is the most complaining borough in New York. Now, that might not be fair. Perhaps there's more people in Manhattan, right? So let's divide by how many calls they get overall, right? And how many 311 calls you get. It's kind of a representative of the total. But even if you do that, so you can do that, you can just get, okay, let me get all the values of boroughs at all the noise data, so just the noise data, then all the data, and just normalize that, and over B. So I can do element-wise computation here too. So this is value counts, other value count, and I get a list that wasn't, because it isn't, the value counts are ordered, but when I manipulate it, they're not necessarily ordered. But it turns out that Manhattan is 0.07. So a lot of things happen in this slide. These value counts give me a little series, right? The series have labels, but the order in which the labels are occurring depends on the values. So the ordering of N counts and B counts might be different. Manhattan might be in first spot for the first, and might be in the last spot for the last. When I do my operation there, they are still matched. All of this sort of magic happens because I always keep track of these labels. So the little bit of extra effort of putting in the labels can be very useful to do your data analysis, because the labels are what give you your meaning. So still Manhattan wins, it seems, 0.0377. And just as a sort of a last example, within Pandas, and we're not even going to touch that much, there's a whole bunch of things you can do to visualize your results. A lot of objects have a dot plot method, and this is no exception. And so I can just say, well, let me just plot these things. Ooh, there we go. Instant plotting, instant visualization. And Manhattan obviously is on top. So any questions? So I know this must have gone a little fast, and that's fine, because it really is more of a demonstration. There's good documentation. Use the help functions of Pandas. Do some Googling, but that's sort of the flavor of it. It's data frames, missing data, labels. Things get matched up. You can add things. You can read all kinds of formats, and you can plot stuff. Okay. So since this was a brand new lecture, I still have to come up with homework. So I'll send that around later. Okay. Not much later, hopefully, by all these. So, questions? Yeah. And there's probably a package for that. One of those packages that I mentioned you have to install essentially does that. But if you're going to do that anyway, you're probably, I mean, then it's in a format that's ready. Now, you always want to check how it read things in, right? If it's just a simple table, it'll be fine, right? But if it's two tables offset by some funny things and comments over there, I don't know what it's going to do exactly. So, yeah. Yeah. So yeah, and it's yeah. I think so. Yeah. 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 Right. That's right. Well, so the order of the rows you shouldn't really think of as being particularly important because they all have labels, right? So you can ask it to sort it by that row. So if you want it back, so let's go to that example again. Yeah. So you could remember we saw how we can sort by a certain label. You can also sort by index if you want. So you can have it sort by index, and then two of the zeros should pop up in the top, and you'd see more clearly what is wrong. Ideally, you'd want to try and avoid this. So that's right. So if you do ignore index, it creates an index for you, or you can you could give this a name. So you see how the column there, XS3, it has a name. The name is 3, so it sounds like it is just the index, but that is its name. So I can give this a name as well. So I can say columns, and I can say name, and then that would be whatever that is. So I can make this 17 by giving it the name 17. Okay? Just a better way to. Yeah, well, it is in there. You just have to get it from its package manager. There's a package manager that you. Oh, you didn't get the academic license? The academic license is free. You just have to sign up with your Toronto account. You don't have that account? Okay. You can still install it with pip install though. So the pip install one, you just have to go to a prompt and type pip install pandas, and that should still work. But then it doesn't come from, yeah, it'll work within Canopy just fine. So there's I forgot where it is, but somewhere in Canopy there's a link, open a prompt. Yeah, Canopy terminal. Yeah. Yeah. Do it from that prompt just in case you had more than one version of Python installed and you want to install it for the Canopy version particularly. But if you have only one version, it doesn't really. Okay. Yeah, you can request it and just so when we apply with our at signet.utoronto, it goes, that's not academic, so it does an extra check, but they get convinced. Whereas the at toronto.ca has been registered as being an academics one already. And it's a bit silly, but no, they have to check somehow. So it's still possible to get. But that just means that the package manager has more packages for you. But this one is so standard that just doing the pip install in the command prompt isn't. Is it? So, oh yeah. For Windows, yeah. Okay. Yeah, so you'd have to do the same thing, yeah. Well, the package is free, it's just not free in kind of thing. Yeah, so if you don't have the license, you'll be doing a few pip installs. But that's, yeah, it's easier to get the license. I think we're all entitled to it. It just might take a little while to convince them. Say, I want it, and then they'll get back to you and say, really, who are you? And oh, I'm fine, working at the university. Okay. Yeah, I think so. So just look at the netcdf module. Yeah, that's the easiest way. There's an NC dump that's very useful just to look at the file without having to open it in Python. So if you have an netcdf file and you install this NC dump from a command line, you can just say NC dump and the file name. It dumps the whole thing. So don't say that because it's a lot of data. If you just want to read the sort of what's in it, you do nc dump-h for the header, and it'll give you all the variables that are in there. And then you know, and that's kind of useful because then when you load it into Python, you know what variables to ask for. It's not impossible to do that in Python as well, but it's trickier. Okay.
Say our private giant CNC.
People say Pandas is faster, but I don't have any benchmarks to show that it's true. It has a few more bells and whistles than over the R data frames, but well, it's right there in R already, and it's built in. And so it's not that they are not there in Python. There's a package called stats models or something, which has a lot of that functionality too, but it's yet another package. And I think most of them work nicely together with Pandas. But it's in R, you just sort of get that for free. So when it works in R, it works without packages for the most part. That's nice. And that's why R is useful if you're doing a lot of stats. But it's less and less true that you have to do it in R, because there's always a package for it. All right. Thanks. So yeah, we'll post the homework, and then if you have more questions, or if you want to, we'll still have office hours next Wednesday, just in case you want to come by, or questions, email us.
Can I just ask a quick question?
Sure.
So for the FFmpeg, so I'm on Windows and I downloaded it and it works on my actual command prompt in Windows, but Python doesn't like it. I don't know if it's because I'm not putting it in the package. This is an example the slides it said to open so I did that. In here was just, it said ffmpeg.exe, and I tried that and it's saying no. So I have no idea how to get and it's weird because I can get the animations to work.